orchestration is basically the process of, given a target sound, finding an orchestral score that most represents that sound. So what that means is you can have a target sound. It doesn't need to be musical in nature. It can be the sound of, like, we'll see water droplets or a car horn. It can be a nature soundscape, of birds and bugs. It can be any arbitrary sound. And then what you want to do is you want to find which instruments playing what notes at what dynamics would most represent that sound. And really what this is it's trying to recreate the timbre of a sound. So I'm not sure what musical background people has, so I'll explain. Timbre is basically the quality of a sound that is the reason when you hear the same note played on a piano and a violin, they sound different. So it's basically, it has to do with what frequencies are being played on any given note. And it's kind of what we call maybe like the spectral profile of a sound. And it's how we perceive those differences and why different instruments sound differently. And what's interesting about it is there's no way of quantifying timbre. So we can quantify things like pitch, each pitch has a specific frequency in hertz. We can quantify volume as, amplitude can be quantified as decibels. But there's no number measurement for timbre. We can't say that one sound has a higher timbre value than another. That just doesn't exist. So trying to recreate the timbre of different sounds is a really both interesting but difficult problem. And this software, computer-assisted orchestration, is a kind of sought-after problem for composers who are looking to kind of have this helpful tool with their composition. We're not trying to replace composers at all. We're really, this isn't us, trying to say like, oh, we're gonna just have a computer make music and that's gonna be it. This is really a tool that is a creative process that aids composers, helps them with their work, maybe gives them new ideas. It's certainly not replacing them by any means. So I want to start by talking about this software called Orchidea. So Orchidea is a software created by Professor Carmine Cella, who is, he's the professor at Berkeley that I'm doing all this work with. He's my advisor for this project. And he's created basically what is the state of the art in computer-assisted orchestration. It's a software, you can download it for free, orchidea.org. There's a set of command line tools. There's a Max MSP package. There's also a standalone application. And it lets you input any target sound that you'd like, and it'll orchestrate it for you and give you a score of the solution and a sound file of the solution. So I want to just kind of start our talk on this by listening to two targets and two solutions. So this first target sound is a kind of piano sequence. So we'll go ahead and listen to this. Okay, so we have this piano phrase, and we input it to Orchidea and tell it to orchestrate it, and this is the solution it comes up with. So I think this is a pretty incredible kind of representation here, that, it can take this piano note, these piano notes, this sequence of chords, and turn it into this orchestral combination. But like I said, this isn't necessarily the purpose of computer-assisted orchestration, because if you want to just take a sequence of piano chords, there's other methods and softwares you can use to, do chord recognition, find the fundamental frequency and recreate it that way. But really the point of computer-assisted orchestration is to take sounds that are inharmonic, who aren't necessarily created from orchestral, aren't created by instruments, and find an orchestral representation of them. So the second target is this recording of water droplets. Okay, so we take this obviously very inharmonic, more noisy sound, and we tell Orchidea to orchestrate it, and this is the solution. So I think this is a great example of kind of the power of Orchidea and what it's able to do. And then the research I'm going to be talking about today is kind of jumping off from this. So Orchidea is software that already exists. And it has a very, like the kind of method it uses, it has a lot of pre-processing steps. It uses like evolutionary algorithms to orchestrate, and then there's a couple of post-processing steps. So the work that I've set out to do with Professor Cella is to see if we can design an end-to-end neural network that does basically this entire orchestration process. So whereas Orchidea might have 8 different steps, from start to finish, we're going to just say, can we put a target sound into a neural network, and can that output an orchestration? So this is our approach. So like before, we have our target and our score, and we're just putting this trained neural network in the middle that's trained as a classifier. So what we're training it on is combinations of orchestral samples. I'm going to get more into that. But what we're going to do is we're going to train it on many different orchestral sounds played at the same time. And we're going to train the classifier to then find which samples were present in that data. So it says, okay, classifier says, there was a flute playing a G sharp in there. There was a clarinet playing, C4 in there. These are the notes and instruments I heard in there. So I want to start by talking about our data. So we use the TinyCell database, which is a collection of 1,500 recordings from 12 different instruments. And each sample is one instrument playing a single note at a specific dynamic. In dynamics for this, if those of you who aren't necessarily aware, I'm not sure how many people know much about classical music, but we have 3 levels of dynamics here, which is the softest is pianissimo, in the middle we have mezzo forte, and the loudest is fortissimo. And I just want to mention, this is a subset of Orchidea Sol, which was a much larger library of recorded sounds that was created specifically for Orchidea. And it has, for example, like we heard with the water droplets, all those plucked pizzicato sounds, those are in Orchidea Sol, but not present in TinySol. So one thing we do that I think is a little bit unique is we actually create the data that is input to our network. So we're not just taking individual samples and putting them in the network and saying, can you classify this? Because we're not trying to get an instrument classifier or a note classifier. We're trying to get a network that can take a complex combination of many notes and many instruments and deconstruct it into its constituent parts. So for example, we're going to take 10 randomly selected samples. So it could be, flute C4 playing at mezzo forte, trumpet G sharp 3 at fortissimo, oboe F5 at pianissimo, and so on. And we're going to combine them to all play at the same time, and we're going to crop it to 4 seconds in length. And then we're going to take the MEL spectrogram, and that's going to be what's input to our neural network. It's that MEL spectrogram of the combination. So I'll talk for a minute about what the Mel spectrogram is. So the spectrogram of a sound is a way of representing audio that has time on the x-axis and frequency on the y-axis. And then the intensity at any given frequency and point in time is given by the color. So the Mel spectrogram is a special version of the spectrogram where the y-axis, the frequency, is scaled to fit the Mel scale. And what the Mel scale does is it tries to map frequency to a more perceptual scale. And one thing that you may not know is the distance. So if you heard a note played at 512 hertz, and then you heard a note played at 1024 hertz, the distance you would hear in between those notes, that interval, would sound the same as an interval between 1024 and 2048 hertz. And that has to do with kind of this logarithmic scale of how humans perceive frequency. So the Mel scale basically takes what would normally be a linear mapping in hertz and converts it to this logarithmic scale that's more similar to how humans perceive sound. The reason we chose this is because really, if you think about what we're going for, we want our solution to be as perceptually similar to our target as possible. While we might try to apply a numerical measure of how close our solution is to our target, really what matters in the end is to a human, does our does our solution sound like our target? Is it perceptually similar? So for that reason, it makes sense for us to apply this kind of perceptual method of representing audio. And so this Mel spectrogram is of a violin playing a G sharp 3. So this is just one instrument playing one note. And we can see this is our fundamental frequency down here. That's going to be the frequency of a G sharp 3. And then what we have above it are what are called the partials. So these are going to be, for a harmonic sound, they're going to be integer multiples of the fundamental frequency. And that's what we kind of call this whole thing is kind of what we call our harmonic spectrum. Now, if we look at the Mel spectrogram of a combination of two samples, we're getting a little more complex picture. So we're going to have our two fundamentals down here, but then the upper partials are starting to maybe overlap in some places, starting to get a bit more complicated. What's also interesting about this is to look in the very beginning, we have the onset here. So this kind of noisiness in the beginning of the data is from the onset of the notes. So, every instrument has a specific onset. So this could be, like a trumpet is going to have a kind of noisier onset at the beginning. And that's what we're getting in the beginning of this data here. But this isn't what we input to our network. What we input to our network is the combination of 10 samples. So this is the Mel spectrogram of 10, randomly chosen instruments and notes being played simultaneously. And as you can see, it's way more complex than just having one sample. So, we might have some fundamental frequencies down here, but really, we can't pick out we can see stronger intensities here, but it's much harder to pick out specific partials. But this is the task that our classifier is suited with, is taking this really complex combinations of notes and timbres and trying to deconstruct it into, okay, there's a flute C4 in there, there's an oboe F5 in there, et cetera, et cetera. So that was just talking about how we create our data. I kind of want to just go over the training phase in general. So we input a bunch of combinations of 10 samples, I think, depending on the architecture we're using, is anywhere from 200,000 to 400,000 samples per epoch. We're inputting that to our classifier, and of course that's outputting a label. So this label vector is going to be of length 424 when we're using 10 instruments. And each index in the vector corresponds to a specific instrument and note. So the first index might be violin E4. The second one could be violin F4, violin F sharp 4, violin G4. And then what we're doing is we're just taking the same indices that have ones in our label vector. These are correspond to the samples that are, present in that, it's what the network thinks are the instrument and notes that are present in the training data. So then after we train these networks, we use them for orchestration. So it's kind of like, you can think of this as like the test phase of our network. So now we're inputting a target sound. We're no longer inputting a combination of instrumental samples. We're inputting like our water droplets or our car horn. We're putting this into the classifier, and again, we're getting a vector of probabilities. And then we're going to take the top 10 probabilities. We use 10 because our training data is made of combinations of 10 instruments. But really, if you wanted to only have 5 notes in your final solution, you could take the top 5, you could take the top 20, etc. So we're taking these top 10 probabilities, and then we're mapping them to their instrument and note that they correspond for. Then we're going to combine all of these together to be played simultaneously, and that's going to give us our solution as a sound file. And we're also going to use them to create an orchestral score as the solution. So there was one thing I kind of glossed over, which was how we do dynamics for the orchestration. So there's kind of a problem that arises when we try to use dynamics, which is that if we have every class for here, this class is violin E4. If we wanted this class to be violin E4 pianissimo, and the next one be violin E4 mezzo forte, violin E4 fortissimo, we would only have one tiny sol sample for each class. So having one piece of data for each class is not a great way to train a robust classifier. So what we decided to do is during training phase, we just forget about dynamics. Each class is just an instrument and a note. We don't care about dynamics. But when we're doing orchestration, we want to include dynamics in the final orchestration because the tiny sol data, has a recording of flute C4 at mezzo forte, but also flute C4 at fortissimo. So what we do is we just do a simple map from the probability as given as an output from the classifier. And if that probability is from 0 to 0.33, we use the pianissimo version of the sample. If it's from 0.33 to 0.66, we use the mezzo forte version of the sample. And if it's above 0.6, we use the fortissimo version of the sample. So if we're just looking back here, right, we had 0.62, so we used mezzo forte, 0.83 fortissimo, 0.31 pianissimo, etc. And that's the way that we were able to extract dynamics, from the output of the classifier without specifically training it on dynamics. And the kind of logic behind this is that it makes sense that a sample that has a really high probability output, if it has 0.9, as the output from the classifier, it makes sense that that sample should be louder than, for example, a sample that had 0.3. We probably want that to be quieter in the final orchestration. So I've talked now about, our training, how we train the system and how we used it for orchestration, but I haven't touched on the actual neural network architectures that we used. So we used 2 different networks. The first one was a convolutional neural network with long short-term memory. So I won't get too much into the exact details of, the number of filters we used, et cetera. But this diagram kind of sums it up of having 3 convolutional layers in the beginning with max pooling, then passing that through the LSTM layer, and then a final convolutional layer, a linear with dropout and sigmoid at the end. And that gives us our 424 length label vector. So I want to talk about why we chose to use a CNN. As I'm sure many of you know, CNNs are really strong at image classification. And if you kind of think about what our data is, if you think about back to the MEL spectrogram, a MEL spectrogram is essentially a 2D representation of audio. It's like an image version of audio. So we said that it makes sense that if CNNs are successful at classifying images, they should be successful at classifying audio when the data you're using is essentially a 2D image version of audio. And then we included the LSTM, the long short-term memory layer, because LSTMs are shown to be successful at learning long-term dependencies in data. And time is a really important aspect of music and audio. So we need to have this kind of temporal nature of audio represented in the in our classifier. And that's why we chose to put the LSTM in there. And we tried this exact same architecture, but with just removing the LSTM, and that had a lower classification accuracy than with the LSTM. The second architecture we tested was Resonant, which is a residual neural network. This was just a more out-of-the-box model, that had been designed in this paper. So I won't spend a lot of time on it, but I'll just mention the breakthrough of Resonant was the ability to use deep neural networks without running into the vanishing gradient problem. They did this by having this identity shortcut they call, which connecting the input of a layer to the output of a layer. And that allowed them to train really deep networks, like I said, without running into the vanishing gradient problem. And similarly, Resonant was great at image classification. So that was for the same reason we used a CNN, we decided to use Resonant for our task. So I'll talk about how these two networks did. So this whole time I've been talking about combinations of 10 instruments. But we also, we started out with just doing 2 instruments and 1 sample from each instrument. So your training data could be just a combination of a flute note and a violin note, for example. And when we're just having 2 instruments, we found really high accuracies. You can see like 0.84 for CNN and 0.96 about for the Resonant, which we were really impressed with and really happy with. But of course, as you make your problem more complex, and you start adding not only more instruments, but more samples being combined at once, the accuracy, of course, goes down. But even with 10 instruments, we were still happy, with classification results of, around like 75% for Resonant. But of course, the main takeaway from this graph is that Resonant outperforms CNN no matter the complexity of the problem. So the training accuracy was always higher for Resonant. This is the same graph that I just showed you, except it has the breakdown with specific accuracies for each instrument. So what's interesting is if we look at this red line at the top, that's the accuracy for oboe. That's not only is it incredibly high at like 98, 99%, but it stays that no matter the complexity of the problem, which we thought was really interesting. And kind of thinking about why this might be, if you think about the oboe, it's a very high-pitched instrument. It has like that more tone-like quality. If you're listening to an orchestra, the oboe is really going to rise above kind of the texture of the orchestra and be very present. So clearly, this has to do with the kind of spectral envelope of the oboe. So how much energy it has in each of its partials above the fundamental is why we hear the oboe the way it is, and that clearly had an effect on how easy it was for these networks to classify it. Whereas if we look at these bottom 3, these are trombone, flute is the orange one, and this yellow one is trumpet. These 3 were kind of the lowest, by a kind of a large margin, the lowest 3 instruments. And we're thinking with trombone, it's a much lower register. It might have a kind of muddier sound, and also we're going to have a lot of noise on its onset. And the MEL spectrogram is not going to be a great way to classify this kind of data that is going to have noise in it, because it's not as clear. MEL spectrogram works really well when you have these clear lines, like I showed you, that has each partial. So, but that was our best guess for kind of why these instruments would be doing poorly. What's interesting is the orange line is flute. And you think if oboes, being this kind of high-pitched wind instrument, you'd think flute would also do well. But surprisingly, flute did not do well like the oboe did. So our best guess of this was the spectral profile of the flute has most of its energy in the first few partials. And then it has a really high roll off in the upper partials. So it's not going to have as many high energy partials as other instruments. So maybe it was more difficult for the network to detect an instrument that only has a few strong partials, whereas we saw that violin had many partials, the lines of frequency going up the MEL spectrogram. And then a final thing to note from these graphs is just the consistency between CNN and Resonant. So our bottom 3 instruments of trombone, flute, trumpet are also the bottom three in Resonant, and our oboe is up there at the top as well. So this showed to us that like this approach we're going of using a classifier to classify combinations of instruments was working. We have this consistency across different models. So now I finally get to show you what this sounds like. So we tested our models on 15 different targets, and I just have a few of them here. So we'll get to listen to the first one is the recording of a wind harp. And now we'll get to hear the orchestration that Resonant made for that target. So it's certainly not an exact replication. None of them, there's never an exact replication of the target, but it's a pretty faithful representation. We have these mostly lower harmonic content definitely being recreated in the Resonant orchestration. And then what we wanted to do is we wanted to take Orchidea as the kind of state of art for computer-assisted orchestration and compare our orchestrations to Orchidea's orchestrations. So we'll listen to the Resonant one once again. And then we'll listen to Orchidea's solution. So this is an example where I think our model, Resonant, outperforms Orchidea. Orchidea kind of adds these much higher notes and frequencies that aren't really present in the original target. So our next one is the recording of a car horn. And here's the CNN orchestration of that. And it's not exactly the same. You have this kind of very kind of shrill inharmonic sound in these very high notes that isn't exactly the same as in the target. And now for Orchidea's solution. So this is an example where I think Orchidea outperformed our model in the orchestration. So the final target is the recording of a boat docking, and it's a little more interesting of a target. It's not, we would call these first two static targets because they don't really change over time. Whereas this boat docking, you'll hear there's kind of these upper whistling sounds, you can almost call them melodies, that come in. So let's listen to that. So this is going to be a much harder target for both these systems to orchestrate. So we'll listen to the output of Resonant for that target. And now we'll listen to Orchidea's solution. So they're pretty different in that Resonant mostly orchestrated these very low harmonic sounds without getting any of these, these higher pitched whistles that kind of come in and out during the target sound. Whereas Orchidea had quite a lot of that high harmonic content. So I wouldn't say this is necessarily one where one outperforms the other. It kind of actually, it's an example of a target that's pretty difficult for both of them. So that was kind of what we called our qualitative comparison, which is what we did of listening to the targets, listening to CNN orchestration, listening to the Resonant orchestration, and then comparing them to Orchidea's orchestration. We also performed a quantitative comparison, and we used this distance metric that, I talked about not being able to quantify timbre, but this distance metric tries to find the difference in timbre space, if you will, between two sounds. So it's going to take in the FFT of the target and the FFT of the solution. And we have this summation where these delta K1 and delta K2 are going to be either 0 or 1, which means we're either going to have, for each K, which is each frequency bin in the FFT, we're either going to have a term from this first sum or a term from the second sum. So we're going to have this delta K1 is going to be 1, which is going to include a sum from this a term from this first sum, when for a given frequency bin, K, when there's the energy for that frequency bin is higher in the target than in the solution. So this means the solution kind of undershot how much energy should be at a specific frequency. Whereas the opposite, the second term, it's going to be included in the summation when there's more energy in the solution than the target for a specific frequency. So this would be the solution kind of overshooting how much energy should be in a specific frequency. So in our experiments, we used lambda 2 larger than lambda 1 because we want to over-penalize when you overestimate how much of a certain frequency should be in a solution. Because if you think about it, if your solution has a lot of frequencies that aren't present in the target, it's really not going to sound right. You're going to be like, oh, those, like if you think of the car horn, you kind of had these upper harmonics in our solution, but there was kind of an extra note in there that didn't really sound like it should be there. So we want to penalize that. Whereas if you just are undershooting how much of a certain frequency should be there, it's not as bad as having too much or having frequencies that aren't present in the target. And we ran this quantitative comparison on our 15 targets. And I think for this one, for 4 of the targets, our model outperformed Orchidea, meaning it had a lower distance. And we also found that on average, the CNN did better than Resonant for this distance. So the distance between CNN solutions were lower than the distance between Resonant solutions and the targets. So kind of what was the point of all this? Why did we try these 2 different architectures? Well, we found the CNN was generally better at emulating the timbre of the target. So this was more during our qualitative comparisons. We found the CNN solutions generally had a better recreation of the timbre of the target sounds. Whereas Resonant did a better job at recreating the harmonic content of the target. An example of this is one of the targets was a gong being hit. And we knew that that target had the notes of kind of a C minor chord. So it had a C, E flat, and a G were the main notes present in this target. When we looked at Resonant's orchestration as a score, we saw that it had those 3 notes, C, E flat, and G, were all present in the orchestration. So what that means is that Resonant was able to determine which notes were present in the target and then correctly orchestrate them. Whereas CNN didn't do this as much as the time or not to the same extent that Resonant did. Okay, so as I'm kind of wrapping up, some things that there's definitely a lot of future work to be done here. And what these 3 things are different things that Orchidea is able to do that our networks are not yet able to do. The first one is allowing sparse solutions. What this means is that a sparse solution would be you only include as many samples in the solution as necessary. So all of our solutions had 10 samples used, no matter what the target was. But Orchidea allows you to only use, for example, maybe there's a target where 2 samples would be a great recreation of it. So allowing for sparse solutions is definitely something important to add. The second thing is allowing symbolic and harmonic constraints. Symbolic constraints are an important part of computer-assisted orchestration. And what they are is where the user can say, okay, for this orchestration, I want you to only use stringed instruments. And then the output should only use, instruments from the string family. Another example could be, I only want you to use pizzicato playing style. So pizzicato is when you pluck the strings. That's what that in the beginning, when we heard the orchestration that had the sound, the water droplets, those were all pizzicato. And then again, you want your orchestration to only use pizzicato samples in the orchestration. Harmonic constraints are kind of like a pre-processing phase. When I was talking about that gong hit that had a C, E flat, and G in it, harmonic constraints are when you analyze the target and you'd find, okay, there's the three most prominent notes in this target are C, E flat, and G. And then you only allow your solution to use those notes. And this is a really helpful way of making solutions sound the most like their targets. And it's something that Orchidea implements that we do not. The final one, which is a big one, is dynamic orchestration. So those Orchidea, in the very beginning, when I showed you those two examples from Orchidea, those were dynamic orchestrations, meaning the orchestration changed over time. You know, we had, for example, in the piano sequence, we had chords changing all the time, and then the orchestration changing to match that. Right now, this network's only set up for static orchestration, meaning it'll just choose one set of notes, like one chord, if you will, for the entire length of the orchestration. It can't change notes halfway through. And this is an important aspect to add if you want to do any type of dynamic targets like that. Boat docking would have a better orchestration as a dynamic orchestration, because it could start out with these kind of very low notes, and then when that whistling sound comes in, it can orchestrate those separately, and while still having these low notes at the bottom. So that is it from me. Thank you so much for having me here to present, listening to me. If you have any, I'm going to take some questions now, but there's also my email is up there, dz.luke@berkeley. If you want to shoot me an email about SynMat or about what I talked about today, I'd be happy to talk more about it. But for now, I'm going to stop sharing and would love to take some questions in the chat. I see we got some.
Yeah, we already have a few. You want to go over them first before I unmute people, so maybe they can do even live ones?
Sure, sure. Let's see. If you add a piano to the orchestra, does it detect it and make the piano play only? Oh, I see. So not necessarily. And this is looking more at Orchidea with the piano sequence we had. It's not really, like I said, we're not doing instrument recognition, and we're not taking a sample and trying to say, okay, what chord is being played or what instrument is being played. What we're trying to do is finding what timbre is being played, which is, you know, not as well defined a problem. So yeah, when you have just a piano, you're not going to try to just acknowledge, oh, this is a piano sample, let me only use a piano in the orchestration. What you're going to do is say, oh, this is the timbre of this sound. Let me try to recreate that timbre using different orchestral samples. Okay, is there a specific reason for using 10 as opposed to a different number of samples? So in our orchestration, we use 10 samples because our training data was created from 10 instruments being played at the same time. But the 10 wasn't, you know, very specifically chosen. What we, you know, in the graph where I had combinations of 2, 3, 4, up to 10 instruments, we saw the accuracies, you know, decreased over time. We kind of decided that 10 instruments was a pretty complex problem for us, and we were able to achieve enough accuracy in the systems to, you know, be happy with solutions from 10 instruments. So it wasn't, you know, a very like specific choice, but it was kind of a complex enough problem that it was worth solving, but also manageable with what we were working with. Okay, length of the time slices. I think if this was about our training data, that was, we cut everything to 4 seconds. If I think that's what that question would have been about. Yeah. Did you ever consider an architecture containing an autoencoder? Yeah, that's definitely something to think about. I don't think we, at least my personal experience coming onto this project, I think we kind of were looking at a few architectures, like I said, that were successful at image recognition. hence the CNN with LSTM. And then as we were working, we were like, you know, it would make sense to compare this to another architecture. That's how we came up with Resonant. But I think an autoencoder would definitely be an interesting architecture to try, but not one that we have tried yet. Okay, suppose you put in a trombone glide, what would come out? That's actually an interesting question. There's so Orchidea would be able to orchestrate that, and you can actually go on the Orchidea website and listen to examples. That's where I got those 2 examples that I played of the piano piece and the raindrop, and there is an example of a glide on there, I'm pretty sure. So you can listen to that if you're curious. For our architecture, however, like I said, we're just doing static orchestration. So right now you can't change the notes in the orchestration over time. So there wouldn't be any glissando, any glide up in our static orchestration. It's actually interesting. Now I'm curious what it would do, because it would have trouble since you're going to have this whole variety of pitches, right, from the bottom to the top. I'm pretty curious, you know, how it would try to orchestrate that. I guess it would be pretty messy. You'd probably get a very wide range of pitches. Oboe has a really specific, yeah. So talking about the oboe, right? I think because of, like I said, if you look at the Mel spectrogram of an oboe, or like I was talking about flute, like the flute was one with a specific, not having as much energy in the higher partials, but more in the lower partials. And we think kind of these differences in the spectral profile, if you will, of different instruments was the reason that, you know, you had really high accuracy for the oboe, but poor accuracy for the flute. But it's also something that we could definitely spend some more time looking into.
And I think that's the end of the questions, really. I'm going to let everybody unmute themselves if they wish to pose another question before we wrap up.
I had one question about, so like timbre isn't just the different instruments, but it's also like how the instrumentalists play their notes.
Mm-hmm.
So like, how would you take that into account? Just more samples with the different types of notes?
Yeah. So yeah, no, that's a great point. One thing I talked about is when we heard the Orchidea orchestration with the water droplets, we had this pizzicato playing of the plucking of the strings. So that was not in the database that we used. I mentioned it was Tiny Soul. That only has like standard playing style, doesn't have any, you know, pizzicato playing style. So we were just working with you know, standard playing styles for instruments. But of course, adding these more not advanced, but adding different playing styles are, of course, have different timbres. But I think while we haven't specifically tried that in this system, I think it would still work, because in the end, you know, our classifiers don't really care if it's just, you know, the bowed playing of a violin or plucking the string of a violin. It just cares about what the timbre of that looks like. So I definitely think it would still work, and Orchidea has still shown success with different playing styles for different timbres. So I hope that answered your question.
Yeah, it did. And then I actually had another question, which was like totally unrelated to that one. I'm interested if like you looked at kind of not just numerically how these things match up, but also like humans may not actually perceive the same frequencies that are like numerically there. So maybe something that would be kind of numerically optimized might not like sound like the best combo to a human based on just like how much our ears can understand. So have you, I guess, what are your thoughts on that?
Yeah, no, that's an interesting point to bring up. I don't think it's necessarily something that we considered a lot in this. The one thing that comes to mind is with the spectrum, scale. I think that can might address that problem in some ways, that we're looking at spectrograms where the distance between notes is the perceptual distance between notes as opposed to the absolute like Hertz distance. But that's definitely, I think, it's a really interesting thing to bring up, and something that could be kind of a flaw in this system of, numerical optimization, like you said, might not necessarily correspond the best to perceptual optimization. So yeah, that's a great question, something to think about for sure.
Cool, thanks.
I have one question. Thanks so much for the talk. It was quite interesting.
Thank you.
Have you considered using other neural networks such as RNNT or transformers instead of Resonant?
I haven't specifically. I'm not super familiar. You said RNNT, and what was the other one?
So there is a transformer attention-based models, and so a particular version of it, which recently has state-of-the-art performance for vision, for acoustics is RNNT,
Okay.
which is from Tara Sinot's group at Google. So that's basically what Google is using for automatic speech recognition. And it apparently uses attention-based structure into the model. Okay,
that's interesting. I was looking at attention-based models a bit, but we haven't tried them with this problem specifically. But thanks for bringing that up. So you said that's Google, like the most recent thing that Google's using for speech recognition?
Yes, and maybe I can do a little bit of an advertisement. The author of that paper will give a talk on January 12th, and I think we can distribute it to people in Rise Lab as well.
Great.
So that's what they're using for when you're talking to Google Translate, or when you're talking to Hey Google, for example. That's what they're using.
That's awesome. That's really cool. Would you mind just sending the names of those architectures in the chat because I'm interested in looking more into them. Thank you for that.
If we finish before this, because our time has just expired, and anybody wants to get in touch with Amir, please send me an email. You can see my email in the announcement, and I'd be happy to put everybody in contact. So I think we need to finish at this point.
Sure.
Thank you so much, Luke. This was a fascinating talk on many levels, and I hope we'll do some more in the future. One thing that I really hope we had some time for is to hear a piece of your music. But unless you have something ready right at your fingertips, I think we'll leave that for some other time, or maybe.
Yeah. Thank you for that. I'm not as much of a composer as some of the other people at SynMat. But I encourage people to, I guess mostly once things are back to normal, come by for a concert at SynMat. It's a center for new music. And if you're not familiar with new music, it's really interesting. There's a lot of stuff, people using extended techniques with acoustic instruments, people using electronics in their acoustic compositions. So if you have any interest in that, come by a concert there, and once things are happening again.
Hopefully we will all do sooner rather than later. Thank you again, and thank you everybody who attended, and until the next social hour talk.
Yeah, thank you.
Thank you so much, Boban.